first one is yt equal b0 b1 xt1 b2 xt square plus u2. So basically we have four models. So discuss which of these are linear. Discuss the relationship between the second and third equation and the distribution of the errors. So which one do you think are the linear models? Is first one linear model? So until now, so let's go back to big picture. We learned linear regression model. So it is basically we are investigating the relation between dependent variable and independent variable, and we are interested in only linear relationship, like y equal alpha plus beta x. So it is linear equation. Okay. But question is whether we know there are a lot of non-linear patterns in the world. So natural question is whether linear regression is enough or not. And the answer is linear regression is surprisingly flexible. So let's take a look at the first one. So yt equal beta 0 plus beta 1 xt1 plus beta 2 xt1 square plus u2. It is non-linear model, right? It is a square quadratic model because we have x square. But we can regard this one as a linear model, right? Simply we can define xt squared as another variable like g, right? Then there is no problem of running the regression. We can simply run regression as we learned, right? So we can use our technique as before. Let's take a look at the second one. Log yt equal alpha 0, alpha 1 log xt1 plus alpha log xt2 plus ut. And it is, of course, not linear model, right? It is log. We have log functions. But again, we can simply regard the second equation as a linear model too, right? We can simply regard log yt as a dependent variable and log x1, log x2, we can regard it as another simply independent variable, and we can regard this whole second equation as if it is a linear model. Still, we have no problem of identifying coefficient. Third one, yt equal gamma 0 xt1 gamma 1 xt2 gamma 2 u2. It is this type of function is very popularly used in economics. Of course, this one is non-linear model. But again, if we take log of each side, then third equation becomes the second one, right? So even though the third equation is not linear, but still we can use linear model to estimate. But there is actually one problem. What is the problem of taking log of this equation and estimating this one? What do you think is the possible challenge of doing that? We cannot take log of a negative number, right? So if this error term becomes negative, then we cannot take log. So hidden assumption is that this u2 term is always positive. So yt never become negative. That's a hidden assumption. So if we compare second and third model, this ut is actually log of the ut. And about fourth one. Fourth one is if we add error term like this, not the first one, then it is possible that, so we have more freedom about assuming the error term of the ut, but this fourth one is, there is no way to transforming this fourth equation into linear one. So this one is truly non-linear model, and it is actually difficult to estimate this one. Not that difficult, but we cannot use linear regression about the fourth one. So again, punchline is that, baseline is that linear model is not that restrictive assumption. By small transformation, we can change non-linear model into linear model, and we can use the technique we have learned. Next, dummy variables. Example, wage. Dependent variable is wage. And let's assume the relationship log WT. So log wage is linear combination of beta 0. So constant and beta 1 at education level of the education, and age, gender, race, black, white relation, and urban, whether they live in rural area or city, and south, whether they are from south or north, and whether people are disabled or not. And then, of course, about this gender variable, then it is a binary variable. Binary, this type of variable is called a binary variable. So like wage, in case of wage, small number means small wage and large number means large wage. So there is natural ordering. But about man and woman, we cannot order between man and woman, right? It is not the, there is no natural value. It is just a category of the human. So in this case, when we want to analyze the effect of gender, what we can do is we use variable called dummy variable. So because it is binary variable, so we can, for your code, man, when an observation is man, we can define this gender as 1 and female it is 0. Right? 1, 0. It is binary, so 1, 0. Then the question is, how does beta 3 means? What happens if we change the meaning of the sex? What happens if we include the dummies for both sexes? Okay, let's do it one by one. Suppose we make gender variable like male 1, female 0. And suppose we run the regression and estimate beta 3. What would this mean? In this case, if it is a man, then male, female. So suppose this one is 1. Then once we run the regression, then log wage becomes basically beta 0 that we estimated, plus let's discard the other one, and beta 3, something like that, blah blah blah, right? Of course, we had hidden number 1 multiplied by 1, right? But if we are investigating female, then the function would be log W equal beta 0 hat plus beta 3 hat 0, right? And other variable. Suppose other variables are the same, then we can basically subtract this one from this one, right? Then all others cancel each other, and only this one survives. Right? So basically, we can interpret beta 3 as a wage difference. More accurate, log wage difference between male and female. How much male would receive more if an observation is male? Something like that. Of course, since it is a log difference, so the real meaning is that if we subtract each other, then log W male minus log W female, and it would become like a beta 3. And then because it is log, so in the end, what we have is, it is basically male and wage female, and exponential of the beta 3 hat. So in other words, basically beta 3 denotes the ratio between female wage and male wage. And the exponential of beta 3 is ratio between female wage and male wage. Now, discuss multi-valued variable like race. Okay. For gender, it is easy. Only two binary category, either male or female. Every human being is either male or female. No problem. But in case of race, there are actually more than two races. White, right? Afro-Americans, Asian, something like that. Latinos, right? And there are more than races, more than two categories. And in this case, we have to be smarter than that. In this case, in case of multi-valued variable like race, what do the coefficients mean on each W variable? What do you compare with of the two races? What happens if you change the base group? In that case, what we can do is, okay, suppose there are three races, okay, Asian, and then white, and black. Then basically what we can do, we can generate those three categories. And basically our strategy is to change the multi-valued variable into the binary variable. So for each observation, like 최보경 학생 and 이은하 학생, and then 유태석 학생, suppose in each observation, they are either black or not, right? Suppose 유태석 학생 is Afro-American, then 유태석 학생 has a value of 1 here. Since he is Afro-American, he is not Asian, so 0, 0. If 최보경 학생 is white, then 최보경 학생 is definitely not black, not Asian, and white. If 이은하 학생 is Korean, then she is not black, Asian, white. So basically, we are transforming multi-valued variable into binary. Either he is black or not, Asian or white or not. So we can do this regression. So in this case, beta 3, this beta 3 has more than one beta 3, right? And here, but there are very important issues related to multicollinearity. What happens if we include dummy variable for both sexes? So in that case, in the previous case, okay, I define one variable which is called gender and give value 1 if male and 0 female. Another possible strategy is we can generate two dummy variable like male, female. So 최보경 학생 is female, not male. Okay, 유태석 학생 is male, not female. Okay, so another strategy is we can use both dummy variable. In this case, actually, we cannot. To answer it, we cannot include both dummy variable. We have to do like this, because if we include both male and female, then if we combine male and female such that simply by adding male plus female, then it becomes 1 to every element, right? Then it becomes exactly same to the constant term, right? So by the linear combination of male and female, we generate constant sum. So this is perfect multicollinearity. So we cannot run the regression. So basically, we have to drop either this one and this one. In this case, I define male 0 and female 0. So in this case, I call female as a base case. So beta 3 note what is the change of weight if we deviate from base case from the base case. So in this case, since base case is female, beta 3 denote what is the difference of weight if we deviate from being a female. Okay. So we cannot include both of them. Race is exactly the same. We cannot use all those variables. We have to drop one of them. Right? So suppose we drop Asian. Right? If we include all white, Asian, black, and if we do the linear combination of these three, by simply adding those three, and we generate 1 for every observation, then it is again just constant. So there is perfect linear collinearity. So what we have to do is we have to drop one of the dummy variable. Then the interpretation is that in this case maybe we have in the PDF file we have beta 4. So it is basically beta 4b, beta 4y. So once we do the regression, what does beta 4b means? Coefficient for this line means what is the incremental wage from incremental wage of deviating from Asian and becoming a black. Okay. Interpretation of the coefficient for y means what is the increment of the wage. Basically, wage differential between Asian and white. Right? So when we use dummy variable, we have to be careful not to include every possible category. We have to drop one of them, and second, we have to be careful in interpreting the coefficient. Coefficient is not simply coefficient does not mean the simply wage of the being a black, being an Asian, being a white. The coefficient means what would be the increase of the wage by deviating from Asian and becoming a black. What is the incremental wage of being a white while deviating from Asian? So it is wage difference of black versus white, black versus Asian, or Asian versus white. So we have to be careful about the interpretation. Now discuss interaction of the gender and the race. What do the coefficient mean? What happens if you change the race group? What happens if you include too many dummies? Okay. So next, another interesting idea is we can do the interaction of. Okay. In this case, maybe one interesting extension of this model is we can multiply gender and race with gender and race and define as another new dummy variable. Right? So in this case, if we multiply this race and gender, in case of 최보경 학생, she will have a value of 1 if for the dummy of female multiplied by white. Right? So we multiply this one. Okay, actually. Now we have to drop 1. And this one should be gender. So we do the interaction such that we multiply this one, and then we can multiply this one, and this one. So multiplication of that one and that one, in that case, 최보경 학생 will have 0, value of 0. For interaction term between gender and white, 최보경 학생 will have still value of 0, right? 최보경 학생 is not male, so male dummy is basically 0. And although 최보경 학생 is white, multiplication 0, 0, 1 should be 0. Right? But 유태석 학생, in his case, his gender dummy is 1. So this gender dummy multiplies. If we multiply this gender dummy into the black dummy, then he will have a value of 1, right? But if we multiply gender and white, then his dummy will be 0. Right? Even though he is male, so gender dummy is 1, but still he is not white, so value of 0. Right? So okay, suppose we do this interpretation, and if we estimate the coefficient, what will this mean? That means in case of the gender and black dummy, if we multiply this one and this one, what the coefficient would mean is that it is wage differential, right? From the base case, such that what is incremental wage of being a black and male together. Okay. interaction of the gender and white is increment of wage of being a male and white together, right? So it is like subsection. Also, we can do those things. We can even interact like gender, race, and education, all three together. In this case, it is the wage, incremental wage of being a male and being a either white or black, and then with certain level of education. Why don't you take 15-minute break? So homework, undertake PCA with stock return data here. So if you click here, you can download the PCA CSV file, COSP 200 data CSV. And if you click this, then, oh, what is going on? They are names of the Korean companies. What is going on? I think maybe if you use your browser, maybe it is okay. So, their name of the forms. So just in case, I'll add another sheet. Add sheet. 아이고. Delete. Rename. So returns and names, and then let me get this one. So you can click either this one and this one. Okay, so anyway, the name of the forms. I think a second rank would be okay, but first one is easier to download. And then use correlation matrix. There are two ways to do the PCA, either covariance matrix or correlation matrix. I want you to use correlation matrix and extract principal component whose eigenvalues are greater than 1 and generate cumulative plot for those PCAs. Yeah. And then interpret each PCA. So for each PCA, you have to analyze factor loadings or eigenvector. And then please do your best what each PCA means. So you can interpret PCA like I did. In order to interpret PCA, as I did, just go to factor loadings and then check those factor loadings or eigenvector, element of eigenvector that has a large absolute value. Okay, done. Okay, now joint test of several regression coefficient. Example 1, likelihood ratio test. Let our model look like this. Yt equal I sum of I equal 0 to n and beta I xti. And then we have another set of variables. I equal 1 to k, so gamma I now zti, and we have a noise error term ut, and number of observation is big T. And suppose we have a hypothesis. Our null hypothesis is such that all gamma I is 0, this one. Our alternative hypothesis is gamma I equal not 0 for all I. So it means there is at least one gamma I that is significantly different from 0. Okay? So basically we want to test like a block of the variable. If k is just 1, then it's easy, right? We can check either standard error or t value or p value, and then if t value is large enough or p value is small enough, then we can say it is statistically significant, so we can reject null hypothesis. But now we want to check block of the variable, so there are more than one, right? So why want to check whether block of the k variable are jointly significant or insignificant. So basically equation 1, if we use matrix notation, equation 1 can be written in the matrix form as y equal x beta plus z gamma plus u. Now y is a vector, length is t. X is matrix, length is t, number of rows are t, number of rows is t, and number of columns is n. Z is matrix, number of rows is t, number of columns are k, and u is vector whose length is t. Okay, you know this. And then what we can do is we, instead of running this regression, and we can run this regression too. So our intuition is that if all gammas are 0, then basically it doesn't matter whether we run this regression or this regression. Why? Because even though we run this regression, because all gammas are 0, simply this one goes away. So our intuition is that if null hypothesis is right, it doesn't matter whether we run regression for y equal x beta z gamma plus u, or whether we run y equal xb plus e. The result should be similar to each other. If null hypothesis is rejected, or if gamma, at least one of gamma is significant, then both regression should be significantly different. 모든 i에 대해서 0이 아니라는 거지. 그러니까 그 말은 뭐냐면 at least 하나에 대해서, 그러니까 어떻게 보면 이게 사실은 약간 잘못된 말이고요. 사실은 여러분 고등학교에서 이게 이런 느낌이니까 모든 i에 대해서 0이 아니라 F적이니까 적어도 하나에 대해서 0이 아니니까 적어도 there exists i로 해서 이게 아니라 이거 경험이 있죠. 그냥 이거 비교하려고 해서 쉽게 큰 건데 이분이 그걸 모를 일 없고 정확히 표현하자면 모르는데 이 부분을 놓쳐 있어요. 하나라도 0이 아닌 게 있다는 거죠. 질문 또. So we call this equation as a unrestricted model. We call this one restricted model. It is called restricted because we put restriction that gammas are all 0. So intuitively, if null hypothesis is right, restricted model and unrestricted model should generate basically similar coefficient. Similar coefficient, which means error term of U or E should be similar to each other, right? But if null hypothesis is wrong, if alternative hypothesis is right, unrestricted model and restricted model should generate different results. So coefficient should be different. Therefore, U and E should be different, right? That's our intuition. So let's investigate those error terms one by one. First, we run regression using restricted model. And it is a residual sum of the squared of restricted model. Okay, so we run the regression and we generate error term and we square some error term, right? Basically, error vector E hat. Okay, E hat is, as you know, it is the projection of the Y to the null space of the X, right? Projection of the Y into null space of X, which is I minus PX. Or it is the difference between Y minus projection of the Y on the space of the X. Space spanned by X. Right? This is what you already know. Or simply it is just Y minus X B hat, right? But B hat is simply X prime X inverse X prime Y. So it is P matrix. So it is I minus P Y minus PY. For unrestricted model, basically we run this regression, right? Everything together run regression, and we collect the error term U hat, and we sum square U hat. So R as a residual sum of the squares of unrestricted model is U hat prime U hat, in which U hat is simply regression of the Y, projection of the Y onto the null space of both X and Z. Or it is a Y minus projection of the Y on the space spanned with X and Z. Or it is simply Y minus X beta hat minus Z gamma hat, as you know. It's something you already know. Then RSSR minus RSSU is E hat prime E hat minus U hat prime U hat. Then it is Y prime I minus PX Y, right? Because I minus P is also projection matrix, so it is idempotent. So I minus P multiplied by I minus P is just I minus P, as you know. So anyway, RSSR is Y prime I minus PY, and RSSU is Y prime I minus P XZY. Right? And then we have Y prime and Y for both parts. So we put this together. So it is basically Y hat Y prime I minus PX minus I plus PXZ, but we have two identity matrices, so they cancel each other. So basically, this is Y prime PXZ minus PX and Y. Right? And then this one should be greater than equal to 0 always. Right? Okay, why shouldn't this one greater than equal to 0? Can anyone tell me the intuition? We can prove this one mathematically, but intuition is actually better. Why do you think it is greater than equal to 0? 엄재민 학생. Why? 백승엽 학생. Why it should be greater than equal to 0? 네? No. Just tell me the intuition. Okay, I'll simply tell you the answer. So basically, E hat. Okay, E hat is the projection of the Y onto the null space of the X, right? U hat is a projection of the Y into null space of both X and Z, right? So which one should be greater? Null space of X or null space of both X, Z? Which space should be bigger? Huh? X, Z? 그 반대죠. It's the opposite. Okay? So there is a space and null space of X is a space other than X. Okay? Null space of XZ is there are space and space other than X and Z. Right? So null space of X should be greater than null space of the space spent by X and Z, right? So this is greater. So regression on the bigger space should have a better fit, right? The difference between the original Y matrix and the projection image should be smaller because we have larger space, right? Right? So basically, so this one, right? This one should be regression on null space, so that one should be smaller in some sense, right? So length of that one is smaller, so that one is bigger, right? So the difference between this and this should be always greater than equal to 0. Right? That's the one geometric interpretation which is I prefer. Second interpretation is, of course, we can compare E hat and U hat. So E hat is the in order to calculate E hat, we consider only X. For U hat, we consider both X and Z. So we use only one set of variable. For this, we only use two set of variable. We use two set of variables. So in that case, the error term should be smaller, right? So this one should be always greater than this one, right? It is impossible that this is greater than U hat prime U hat is greater than E hat prime E hat, because in that case, at least we can drop. Okay, in that case, gamma will become 0 anyway. So that is subset anyway. So always this one should be greater than this one, right? Okay, let's compare these two models. We have one more variable, so this one should be better fit than this one, right? Because we use at least one more variable. It is impossible this is better fit one than this one, right? At least if it is not important, we can simply put 0. If we run regression, if it is not important, it will generate 0 anyway. So the error term from this model should be greater than this one always. Right? Therefore, this one should be always greater than this one. Right? 그림으로 설명이 가능하지. 네, 그것도 설명이 가능하겠지. 수직? 네, 이건 오스도고날 프로젝션이지. 넌 오스도고날 프로젝션도 배울 텐데, 이건 항상 오스도고날 프로젝션인 거죠. 질문. 아니 그러니까 이건 아이덴티 벡터 더할 때 이것들이 서로 캔슬 아웃 되는 거죠. 이렇게 이거하고 얘하고. 아 그러니까 그렇지. 이 햇이 이렇게 생겼잖아. 그러니까 이 햇 프라임 이 햇은 y 프라임 i 마이너스 p 프라임 i 마이너스 py지. 근데 i 마이너스 p는 프라임은 i 마이너스 p하고 똑같죠. 예, 사인 매출이니까. 게다가 또 i 덴포턴트니까 i 마이너스 p i 마이너스 p는 i 마이너스 p하고 똑같은 거지. 그래서 이걸 그래프로 설명을 해보면 그러니까 봐봐요. So okay. 이거 3-dimensional. So how can I? 그러니까 이 1차원상에 그러니까 일단 2차원으로 설명을 해보죠. 3차원으로 설명을. 네. So suppose we have two independent variables, two information, and suppose this is y, and if we do the regression, okay, this is, so we orthogonal do the orthogonal projection. So this one is image of the y on the space spanned by x1 and x2, and we call this one y hat. So y hat is image of y on this space, which is p y, right? So if it is good fit, then the distance between smaller and smaller, right? If the distance between this one is, if this is smaller and smaller, then this y hat become longer and longer, right? So if we have a good fit, then let's take a look at this triangle only, okay? If it is good fit, then y hat, and if it is a bad fit, okay, in this case it is y hat and y, okay. So if we have a good fit, okay, then this is small, this is large. If we have a bad fit, this is large and this is small, right? So in this case, we can take a look at everyone, but let's take a look at this one first. So y prime p x z y. So it is basically square of the y hat square, right? So basically it is the square of this one, right? But if we use space larger than, so in this case, we regress y on the space x and z. In this case, we regress y on the space x. So space x z is larger. So we do the regression on the larger set. So in the first case, this one should be longer than this one. Right? So in this case, it is simply y hat prime, y hat square. Basically, we can write down the last one as and this is xz, right? Right, so p square is still p, right? So in this case, it is because basically length of this one, right? So because it is the regression image of y on the space x and z, but space x and z is greater than just space x. So basically, the image of this one should be better fit, right? Because we use two information. So this y hat, this one should be longer than this one, right? So this is like regression on x and z, and this is like regression on x, right? Again, since we use more information, this should be better fit, which means that this is smaller and this is larger. So therefore, y hat prime y hat on xz plane should be longer than this one, larger than this one. So this should be always greater than or equal to 0. Okay. So that is geometric interpretation. This one is opposite geometric information. It is opposite. This one is like opposite interpretation. It is like regression of y on the null space of the x. So null space of the x. So it should be looks like this part. This one is regression of y on the null space of both x and z. But null space of x and z, both x and z, should be smaller than simple null space of the y, right? So actually, yeah, this one is smaller, right? So again, this one is square of the large thing and square of the small thing. So until even if we use the first one, still this should be always positive, right? In this case, we are taking into account, we are investigating space, comparing space spent with x and z and space spent with just x. And it is opposite, null space of the x and z and null space of the x. Right? So it means that, okay, if restricted model and unrestricted model is similar, then I can use your intuition. If you use your intuition, then it is regression on the information both x and z, and regression on information only x. So the difference is regression on z in some sense. So if that remaining information is not important, then this one should be close to 0. If there are huge difference between restricted model and unrestricted model, in that case z part should be important. So this one should deviate from 0. Right? Because in this case y becomes longer and longer. So, okay, that's our intuition. So, the distribution of actually y prime pxz minus px follows chi-square distribution. Actually, we can prove this, but chi-square distribution with degree of freedom k, obviously, k is number of columns in z, right? K is here, right? In z. And the next, for unrestricted regression is y prime I minus px z y. So we know this one has degree of freedom of t minus n plus 1 plus k in this case. Right? So we have a two chi-square distribution, and RSSR minus RSSU should be orthogonal to RSSU. Therefore, this means that since the ratio of the two chi-square distribution is F distribution, therefore, what this means is that RSSR minus RSSU divided by K and RSSU divided by T minus N plus 1 plus K. This should follow F distribution with degree of freedom K and T minus N plus 1 plus K. Right? But again, by the property of the F distribution, if we have a large number of observations, then you can simply drop K, and this entire should follow chi-square distribution with degree of freedom K. And then I didn't explain why this one and this one is orthogonal to each other, but actually it is very intuitive. If we want to use F distribution, okay, F distribution is basically ratio between chi-square distribution, but hidden assumption about F, key assumption about F distribution is that those two chi-square distribution should be independent of each other. And actually intuitively in our case, this should be independent of each other. Why? Why do you think so? Why do you think it is those two terms are independent of each other? Can anyone tell me? Intuition. Tell me the intuition. Okay. Let's go one by one. First, let's take a look at the denominator, RSSU. RSSU is basically this term, right? We regress y on the null space of x and z, right? So it is basically, in some sense, it is regression of the projection image of the y on the null space of x and z. In the case of RSR minus RSSU, which is, as you just noted, is the regression of the y on the space of xz minus x. So in some sense, it's regression on the space of z. Okay, it is just regression projection on the space, null space of both x and z, and this one is a regression on the space of the z, right? So in previous case, it's space z, and this one is null space of both x and z. So it is also null space. Since it is null space of both x and z, it is also null space of the z as well, right? First one is space of z, and second one is null space z. So they should be independent of each other, right? Because they are different space. Right? 아니 수직인 게 아니라 한쪽으로 리그레이션을 해서, 그러니까 이게 우리가 오소고널 리그레이션이잖아, 그죠? 직교 프로젝션이니까 항상 우리 프로젝션 이미지는 직각이라고요. 이쪽이 하면 그게 널 스페이스도 역시 직각이고, 이게 항상 이렇게 직각이잖아, 그렇죠? 근데 이 플레인과 이 플레인은 그러니까 항상 직각이 돼. 우리가 그런 식으로 리그레이션. 그러니까 직각이니까 오소고널 하니까 인디펜던트 하는 거지. 그래서 RSR 바이기 RSSU와 RSSU는 인디펜던트 할 수밖에 없는 거지. 스페이스가 다르니까. 이해가 되죠? So that's why, so they are orthogonal. So in geometrically they are orthogonal, right? No, they are independent. Therefore, we can regard the ratio of the two chi-square distribution as F distribution. Once we can set this F distribution, right, F distribution, then think about what happened to, okay, I can explain this one later. So this is F distribution, and if we have enough number of sample as we learn, it should become chi-square distribution. And if our null hypothesis is right, in the null hypothesis, we argue those information are zero, right? Zero, then this one should be close to zero, right? Because this space is not important anymore. So regression on Z space should be very close to zero as well, right? So if this space is not important, if we regress on the null in this space, this should be very small, right? They should be close to zero. So this one is should be close to zero. Okay, so the value of the f is not statistically different zero. Okay, in this case, then of course we say we cannot reject null hypothesis. We say information z is unimportant. However, if the value of f is large enough, if this is large, then this term is large, which means that regression of y on the space of z is important, which means that this is long, okay? So this is little bit different, long enough, which means that they are important. So we cannot say, in that case, we cannot reject null hypothesis. In that case, we can reject null hypothesis. We reject null hypothesis, and we can say at least one z is important. Okay. So in that case, we should use unrestricted model. So if f value of f is close to zero, then we can use restricted model. We can safely discard z. But if f is large, then we have to include z. Okay. Yeah. 그러니까 스팬은 X의 널 스페이스의 정의가 뭐냐면, 그렇죠? X로 이렇게 스팬하는 X의, 그러니까 뭐 스팬이라는 거 스팬이라는 게 딴 게 아니라 X라는 게 매트릭스가 있잖아. 그리고 여러 가지 변수들이 있잖아. 그렇죠? 이것들이 리니어 콤비네이션으로 스페이스 되는 부분이 이 스페이스는 X의 X로 스팬되는 스페이스라고, 널 스페이스는 뭐 무조건 직각이 되는, 직각이 되는 스페이스의 널 스페이스. 널은 그러니까 다 봐야 되는 거죠. X의 널 스페이스는 X가 오수고나라는 X로 표현된 스페이스에 그냥 근데 계절 수업은 안전하잖아. 이곳저곳에서 와서 보니까. 근데 뭐 내 과목을 이해하기 위해서 선형 대수를 들을 필요는 꼭 없어요. 지금 다 이해했잖아. 딱 이것만 하면 됩니다. 그렇지만 선형 대수를 듣고 다시 이 강의를 듣면 다시 이 강의에서 배운 내용을 리뷰를 하면 아마 훨씬 더 이해하기가 쉬울 거예요. 뭐 선형 대수 들으면 전공 인정해 주고 그런 거 없나? 네. 누가 이걸 말해? 오케이, 그러면 나는 그걸 또 딴 데다 보고하면 되겠네. 학생들이 선형 대수를 듣고 싶기 원한다. 네, 좋습니다. 네. 아무튼 네, 질문 없나요? This kind of the test just I described is called likelihood ratio test. This is called likelihood. Actually, likelihood ratio test is more general concept than this one, but so this is the subset of likelihood ratio test. Okay. Again, likelihood ratio test is now very simple. I explained in detail because I want to explain intuition of the likelihood ratio test. But in practice, likelihood ratio is very simple. You have a two set of variable you are interested in, variable you are not interested in. So you want to know whether you can drop this uninteresting variable or not. And it is simple. First, you include only the variable you are interested in, run regression, generate error term, and square the error term. Second, you include both interesting and uninteresting variable, and run regression, collect error term, and some square error term. Okay. And next, what you can do is just calculate distance. So it is difference between first error term and second error term, and divide with k, number of variables you are not interested in. Second, RSSU is the sum of the square of errors from the model that use both interesting and uninteresting variable, and divide this one with t minus total number of variables in the uninteresting model, and calculate the ratio of the two, and check the table for F distribution, and then you can check whether you can reject this one in like 95% confidence or not. So in practice, it is very easy. And next, world test. Again, unless y equal I equal 0, it is sum of from I is from 0 to n, and beta I sti plus ut. So we have linear model. Number of variables is n. Number of observation is big T. And then consider, okay, now we have another very interesting, okay, hypothesis. Null hypothesis, first null hypothesis is, okay, linear combination of beta I becomes B. So basically it is restriction on the linear combination of each beta. And alternative hypothesis again is rejection of the, it is negation of the null hypothesis. So it is an alternative hypothesis. Linear combination of those variable is different from B. It is null hypothesis. Then how can we use this structure to test if two coefficients are equal to each other? How can we use it to test if two coefficients are proportional to each other? Okay. How can we use it to test if beta 3, beta 6, beta 4? So we can use world test to answer this kind of question. So for example, how can you use this structure to test if two coefficients are equal to each other? So it means, so suppose we are interested in whether beta 1 equals beta 0, then it is easy. What we can do is, so suppose we are interested in whether beta 1 equal beta 2. Okay, if we are interested in this one, then we can simply 1 minus 1 Okay, 0, 0, 0, and then beta 1, beta 2, 0, 0, 0, beta 3, and then you can simply put 0, right? This and these are same. Right? Same. So in this second one, in this case CI is 1 minus 1, 0, 0, 0, 0, and beta and B is 0. Right? So you can use wild test to hold this time to test this type of hypothesis. And second, how we use to test if two coefficients are proportional to each other. Okay? So suppose like this one. Right? So in this case, beta 2 is k multiple of the beta 1. So, right? So in this case, beta 2 and beta 1 is a proportional relationship. We can test this one with wild test. In this case, beta 1 k minus beta 2 should be 0. So you can simply change this as k. Right? So then the question is, so our goal is we want to derive distribution of Ci beta hat on the null hypothesis. So if null hypothesis is right, okay, so we want, in order to investigate distribution of these restrictions, so what you can do is, since we want to test null hypothesis, suppose we have to assume that first we have to assume that null hypothesis is right. Okay, first we can set null hypothesis right, and then later on we want to check whether that assumption is exactly or not, right? So let's assume null hypothesis is right. So if this null hypothesis is right, okay, if there's null hypothesis right, then expectation of this restriction on the null hypothesis should be equal to B, right? Because expectation of Ci Bi hat, right? Bi hat equal to sum of from 0 to n of Ci expectation of beta I hat, but whereas regression is unbiased estimator, so expectation of beta I hat is beta I. So this should be equal to B if null hypothesis is right, right? If null hypothesis is right. And it is in addition variance of the restriction C, which is sum from 0 to n of Ci beta I hat is again equal to sum of I, sum to I, sum j, and covariance of beta I hat and the beta j hat. And actually we know what it is. Right? We already know what they are. It is up diagonal term of variance covariance matrix of beta, which is sigma square x prime x inverse, right? So anyway, in matrix form, null hypothesis is basically C prime B is B. So in this case, this is C prime, this is B, okay? And this is, in general, B in this case. More generally, in our region it's B, but okay, more generally, we can say it is B, right? So in matrix form, we have this relationship. So if null hypothesis is right, expectation of C prime beta hat should be C prime expectation of beta hat, but expectation of beta hat is beta. And this one should be equal to B, right? If null hypothesis is right. And about variance covariance matrix of this restriction, which is D C prime beta hat. And then it is variance. So we can see it's constant. So we can put C outside. Okay. So if we put C outside, then it is C prime D beta hat and C. Okay. Pre-multiply, multiply later. And of course, variance covariance matrix for beta hat is sigma square x prime x inverse, right? So basically it is C prime sigma square x prime x inverse C. Then this is sigma prime, sigma square and C prime x inverse C, right? Okay, this is not related with the hypothesis. This one is related to hypothesis, right? Null hypothesis. Okay, so we use both mean and variance. mean and covariance matrix under the null hypothesis. Right? Therefore, under null hypothesis, C prime beta hat minus B divided by S square root of C prime X inverse C should follow T distribution. Okay? Should follow T. It should follow not G normal distribution. It follow T distribution because instead of sigma square we use S, right? Because we don't know sigma square, right? We use S. Or equivalently, just T square of the basically T distribution is a special case of F distribution. So basically we can write down this way. So C prime beta hat minus B prime S square C prime X inverse C inverse C prime beta hat minus B should follow F distribution with degree of freedom 1 and T minus n plus 1. And note the relationship T and F distribution. Okay? And of course, if we have large number of samples, then T distribution simply becomes normal distribution, which means that F distribution simply becomes chi-square distribution. Right? So if we have a large number of samples, then simply this one becomes chi-square distribution with degree of freedom 1. Right? So basically, F distribution is just square root of this one in some sense. And about more general wild statistics, but I mean in this case, basically we have one restriction, right? Special linear combination of betas have some constant, but actually we can generalize this one. What if we have a k number of restriction? If we have a k number of restriction, then we can investigate k number of linear combination of beta. So now C restriction matrix C is k by n plus 1 matrix. N plus 1 is number of variable and k is number of restriction. Okay, and B is the relationship between beta. So if it is null hypothesis and of course alternative hypothesis, now C prime beta should be different from B. It is almost similar to this example, but now we want to add more restriction, right? So it is restriction between, so like this one. This is first restriction, and we can imply another restriction like beta 4. Right? In this case, let's say it is K. So if we wanna impose both this restriction, then what we can do is we have to expand this one further, and this one 0, 0, 1, minus 1, 0, 0, 0. And this one should be, now we have 0, 0, right? So now, two restrictions. So we have 2 rows in the C matrix. Length of B should be 2. There is no difficulty about this generalized restriction. It is almost similar. So give some example. Okay, I just gave you example. Note that the first example can be written in this form. The special case of C0IK. In the first one, simply it is all 0. Okay. First example, previous example is just special case of this one, because if we wanna investigate only this one, we can simply set everything here is 0, and this is equal to 0, right? So it is special case. So anyway, the logic is exactly similar to the previous one. Okay, expectation of the C prime. Now C is the K by n plus 1 matrix. So expectation of C prime beta hat equals now C prime expectation beta hat. But OLS regression, beta hat expectation of beta hat is equal to beta. So if our null hypothesis is right, C prime beta should be B. Right? So basically expectation, this one should be B. And then we also know various covariance matrix of the restrictions. D C prime beta hat equals to C prime D beta hat and C. And then of course covariance matrix of the beta hat is sigma square x prime x inverse. So it becomes sigma square of C prime x inverse C. Now we have mean and variance, so we can construct the statistic. So first, F distribution. Now on the F distribution, we have to divide this one with number of degree of freedom, and now we have degree of freedom is k for the first one. So first we have to divide with 1 over k, and this one is simply this minus this, and multiply this one before and after, and this is variance matrix of the restriction. But if we have a large number of samples, simply we can disregard 1 over k, and this term should follow chi-square distribution. Right. Any question? Okay. Now, since you learned likelihood ratio test and wild test, so I can give you another homework, which is, so until next week we have to do principal component analysis. So, and another homework is due 2 weeks. So basically, for the second homework, which is due in 2 weeks, you have to reuse the Fama French three-factor regression. Okay. I hope you didn't throw away your previous homework. So first homework, do likelihood ratio test such that beta for size factor, beta for SMB equal to beta for HML. Actually, this I have this. They are same. Can I have a more interesting one? Anyway, I think this is good enough. And second, do world test of the now tweak coefficient whether different or not. Beta SMB equal to beta HML. So basically, in your previous homework, you did a regression of the stock return on the Fama French three factors, right? So you have a constant term and coefficient for market factor, size factor, and value factor. And I want you to test whether the factor beta coefficient for size factor and value factor is same or not. And there are two ways of doing the test: world test and then likelihood ratio test. Any question? No. 질문 없나요? 숙제에 대해서? 오늘 수업한 거에 대해서 질문 있거나 숙제에 대해서 질문 있으신 분? 숙제 별로 어렵지 않겠죠. 여러분이 그대로 한 걸 가지고 한 거에 가서 C만 앞뒤로 곱하면 되는 거니까. 질문. So I assume you have no question. So see you next week. Again, next week we have class. Okay. Thank you. See you next week.